Smash Brothers. No. We're going here.
You seem like a Samus guy. I say fall.
Did we do this one yet? We did part of it, right? So there are about a quarter. We started this one, I know. I don't think we finished it, though. Okay. Well, and D, but we haven't talked about D yet. Something I did not bring up last time we were talking about this one is that this one has the potential given to us. About a quarter of all the problems on the AP exam that are related to Gauss's law give the potential instead of anything about the electric field. So yesterday I spent probably a disproportionate amount of time trying to make sure I imparted to you the difference between this formula for electric field and this formula for electric potential and the limits that you can use this formula. Guys, remember all that? I want to reiterate that the electric potential can only be accessed. This expression for electric potential can only be accessed by a straight path from infinity to your location around your charge. That you have to start from the outside and work your way in. While the electric field can be taken anywhere. It's just your distance away from your charges. You'll notice this problem was really about finding the charge with only the sphere here first, without the shell around the outside of it. And once the shell was out there, they didn't ask about the potential anymore. They try to be careful about asking potential questions because they can be deceptive. What question they didn't ask, and I want you to think about, because I don't know whether you'll understand why I'm asking it, is, does the potential on the inner surface change when the shell is placed on the outer surface? And that's related to question C. Lawrence?
Yeah.
Why? Now, Lawrence is correct, and that's the kind of multiple choice question I think you should consider yourself warned about. It's funny because you didn't change how much charge is here. You merely took this shell and placed it around the outside. But that suddenly changed the potential at the edge of the shell, even though the charge didn't change. And that's because we created a region in space that had no electric field. Now, what's interesting, or potentially a problem, is, did the potential go up or did it go down? Well, be careful. The potential was negative. So maybe I should say it this way. Did the magnitude of the potential increase or decrease? Go ahead. Yeah, I think it does decrease because it will take less work to get a particle now to the center. Now, I want you to think about what that means, because we have to connect some of this to mechanics. When you were bringing that shell together, right, to put it around the sphere, the energy of the system decreased, which means it would pull the shell together. The energy had to go someplace, and it would go into work, and that work would have to be on the shell that was being placed around the outside. That also means that it would take an equal amount of work to pull the shell apart. So when you go to bring the shell there, it doesn't just, it takes energy one way or the other to put that shell around the outside. Since the whole system lost energy, then it would have sucked the shell in and clicked it together. And it shouldn't be a surprise as to why. The positive charges on the inside of the shell would have been attracted to the negative charge at the center. And that would have caused a force on those negative charges, which would be greater than the other charges that were on the outside of the shell. And so it would have pulled the shell into its position around the sphere. And if you wanted to separate them, you would have to do work against that force to get it separated again. This kind of question is incredibly popular on multiple choice. When the energy of an electrical system decreases, then you have to consider the work that was done. If it decreases, it pulls the object in to make the change. If the energy increases, you have to do work to get it together. What's interesting to me is, if you're bringing that shell in, you wouldn't have to push the two pieces together. It would be pulled from your hand and it would lock into place. Yeah.
Wait, why? 'Cause, like, so when...
I gave 3 reasons why.
Yeah.
So pick your favorite.
I'm just wondering, because does it matter if it's not charged, or...
It's a conductor. So imagine this moment right here when the shell is, say, this far apart. And let's consider just one side for a moment. The center is negatively charged. So that means that the electrons in this are pushed to the outside edge, revealing positive charges on the inside edge. Right? What's closer to the center sphere, the negative charges or the positive charges? So there's going to be a force on the positive charges. Now there's going to be a repelling force on the negative charges, but they're further away. So the net force is going to be towards the center. That's what's going to pull it out of your hand. It's doing work on the system, but it lowers the energy of the system. And that's going to remain there. Right? As long as there's a negative charge at the center and the shell around the outside, those negative charges and positive charges are going to be separated. And so it will hold itself together. You will have to do work to separate it. In fact, they go an extra step. By connecting this to ground, they've drained off all the negative excess charges. That too is changing the potential. Because now there's less force trying to push it apart than there was before. And there's a lot more force now, net force, towards the center holding it together. Lovely. You follow? Yes. All right. So, let's go to part C. Determine the magnitude of the potential difference between the sphere and the conducting shell. So first, we know that the electric field out here became 0 after they drained those charges. Right? The electric field moves to 0 as the charges leave the shell. And we know that the charges on the inside of the shell have to be equal to positive Q, whatever this is, and this is negative Q. And you found the amount of charge in the prior part, right? 4.4 times 10 to the... I can't remember, but we need this. What is it? Negative 8 coulombs. And it's negative on the inner shell and positive now on the inside wall of the shell. Let me say, okay, negative on the sphere, positive on the shell. You follow that? Because I kind of stumbled over my words. So I'll do it this way. This charge right here has to be positive 4.4 times 10 to the negative 8, spread out around the entire inside edge of the conducting shell. And this part, right there, is negative 4.4 times 10 to the negative 8 coulombs, spread out all around this shell. Everybody good? All right, so it says, determine the magnitude of the potential difference between the sphere and the conducting shell. Potential difference. So, and we're going to have to calculate this from C to B. Now, luckily for us, the electric field at C is 0. Right? Has to be. We're just inside the shell, but the electric field in the shell we know is 0 and starts at 0 right there at the edge, right there, the electric field is going to begin at 0. Yep. You're going to talk up.
Wouldn't it be from A to B?
No, A is it would be from B to A. You're right. Sorry. Eyes getting old, I guess. But yeah, the inner part of the shell is B. Still, the electric field there is 0. We just get inside the shell. So when we go to do this, we don't actually have much work we have to do, but we do have to use the expression for the electric field, which is KQ over R squared. And again, we're going to evaluate this from B to A to produce what the electric potential is. Now, it's not too much, but in doing this calculation, the K and the Q are constants, and that Q is the inner charge, the negative 4.4 times 10 to the 8th. So this becomes KQ integral of R to the negative 2 dr from B to A. Now, you have to take the antiderivative of that R to the negative 2. Now, we've already done this. We know what our answer is supposed to look like. It's just going to be 1 over R. But for you guys who don't have calculus, something like that. Taking the antiderivative. And if you don't remember, you're going to add 1 to your exponent, and then divide by the new exponent. That's what you get when you go from R to the negative 2 to your antiderivative with respect to R. All right, we have to stop there. It says, imagine a 3-dimensional closed surface whose cross-section in the plane of the page is indicated. All right, gotcha. So that's our Gaussian surface right here. And we're looking at this point in space, and we have 4-point charges. Fantastic. It says, which of these charges contribute to the net electric flux through the surface? It's very important that we read this question carefully. Electric flux only cares about charge enclosed. So Q2 and Q3 are the only charges that contribute to the net electric flux. Let me point this out. All 4 charges contribute to the flux. All 4 of them. But that word net, they are the only ones, only the ones inside contribute to the net electric flux. Remember, the idea behind Gauss's law is it's how much of the electric field is going through the surface. Any electric field from this charge, any electric field from that charge will go into the surface and out of the surface. That's why it's not part of the net electric flux. Can we just get 2 and 3 done real fast? Because which of these charges contributes to the electric field at point P? All of them. All of them contribute to the electric field. If we didn't have that little surface there and I asked you to find the electric field, you would have to find the electric field from that one, the electric field from that one. The surface doesn't change that. They all contribute to the field. That's always been true. It has nothing to do with Gauss's law. And 3, are your answers to 1 and 2 the same? No, they are different. Why are they different? Because the charges still contribute to the electric field, but the electric flux sums the whole surface. And that's why the 2 values are different, 2 answers are different. So when we're talking about part E, net charge. So that's important to realize here, that we're talking about the sum of the charges. They're saying if it's 0, does this mean the field is 0 at all points? No, not even close. All that really means is that you have as much field going into the surface as you have coming out of the surface. Because flux isn't a measure of the field. Flux is a measure of how much of the field passes through the area. And it counts field going into the area different than field coming out of the area. Field going into the area is negative, field coming out of the area is positive. So you can have net charge equals 0, sure, but that doesn't mean the electric field is 0 at all. It just means you have the same amount of charge going in and out. Now, so that one's no. But the next one, if the field is 0 at all points on the surface, does this mean there is no net charge enclosed by the surface, and justify your answer? How do you interpret this phrase? No net charge. Does that mean no charge? That means no net charge. So you could have, this could be plus 1 coulomb, this could be minus 1 coulomb. And right now I have no net charge. But this one's weird. It doesn't say flux. It says if the field is 0 at all points on the surface. Now, I don't think that'd be possible with the arrangement of charges that I have here. Is it possible that you could have an arrangement of charges where the field is actually 0 all around there? Yeah, I think you could. Does that mean that there's no net charge enclosed by the surface? Yeah, it would have to mean that. For the field to be 0, when we look at this, if they say the field is 0 at all points, then the flux is 0. Period. There's no way for the flux not to be 0. Because it means at every single point on the surface, no matter what, there's no electric field. So therefore, there is no flux, period. So you can't get away from the law. That would have to mean that the enclosed charge is 0. The net charge has to be. But it doesn't mean that there's no charges in there. And it was funny because the test writers didn't write this question haphazardly. Some group of people wrote this and then passed it to another committee who also read through it and passed it to another committee who helped edit it. By the time this question actually makes it to the test, it's been vetted a lot. They didn't choose these words unintentionally. Saying if the field is 0 at all points on the surface, they are trying to confuse you. They're trying to see if they can find some narrow place to kind of wedge your understanding of this. And the first thing I want to take away, or at least I want to take away from the test writers, is they want to do that. Sure, let them. Don't neglect the fact that this is a law and is invariant. Meaning regardless of what weird circumstance they put down there, if the flux is 0, the enclosed charge has to be 0. Vice versa, if the enclosed charge is 0, the flux has to be 0. That statement can't be violated because it's a law. Now, you have to understand the distinction that flux equal to 0. So saying that the flux is 0 does not equal saying the field is 0. Those are two separate things. Having a place that's a 0 field does not necessarily mean 0 flux, and vice versa. They had to be super specific here to say that the field is 0 on every point on the surface. That is super overkill. But they said it anyways. Yep.
So if you were actually taking this FRQ, to get the full points for F, you would basically just say because of Gauss's law, when you do this, when we solve the flux, when we solve the electric field is 0, at every point the undergo, so the undergo goes to 0.
Yeah.
And what would you say for E? How would you get the point for the explanation?
Well, again, for E, I would start by saying that when they say the net charge enclosed is 0, then that statement by Gauss's law also equates the total flux to be 0. So, I mean, you need to point to Gauss's law, but what you can't say is it's true because of Gauss's law. You have to explain why Gauss's law says that it's true. So, like I said, E is, I think, the easier one to do because they tell us that the net charge enclosed by a surface is 0. This means that the enclosed charge is equal to 0. Now, justify doesn't mean you have to write sentences. Justify means you have to show by a combination of words, equations, and or pictures why it's 0. Justify gives you pretty wide latitude to make your justification. So you can set this equal to mu naught times E dot dA. And say, well, once I've done that, does it mean that the field is 0? No, it means the flux is 0. But you can have both positive and negative flux that sum up to be 0. So there can be a field. So you have to explain why this isn't necessarily saying that the field is 0. We all good there? All right. Yes.
So could you just say electric field can enter from outside the surface and then also leave?
Yeah. But if you're going to say that, I would make sure you indicate that flux entering is negative and flux exiting is positive, and the sum would be 0. Because they're going to want, saying enter and exit doesn't mean that the person understands that's reading it. They're trying to figure out if you know what you're talking about.
Did you mention that before?
Yeah, you're going to need to put a little bit of the math into it. Go ahead.
I'm a little confused about. So this goes back to yesterday's question, part 2 of D. It said what charges contribute to the electric field at point P1. We said all the charges, but why is it all the charges? Because on the last FRQ, we said by Gauss's law, the outer ring doesn't contribute to the electric field, but why do the charges outside of the surface contribute to the electric field here?
Okay, so I have to be careful there. In the prior one that you're talking about, I didn't say that the outer charges didn't contribute to the electric field. I said that by Gauss's law, the outer charges aren't necessary to calculate the field. That's a different statement. Now, I want to address your statement about the other one in just a minute. Let's look at just this one. If the squiggly line wasn't there, and all I had was, so give me a second. 2, 3, 1, 4.
Conducting shell, non.
If this black line was a conducting shell.
Yeah, if P1 was inside a conductor, would that change the answer to?
0.
Yeah, so it'd be 0. Okay.
Yeah, if that was inside a conductor, it would have to be 0.
Okay.
It's not that it supersedes Gauss's law. It's simply that and I was talking with Carlos yesterday after school about this. No matter what's happening, the movement of the electrons inside a conductor will always force the electrons to rearrange themselves to produce an electric field of 0 inside a conductor.
Would you still say that all of them contribute to the electric field then? Or would you say none of them contribute to, if
Like
it has
these,
the same question-
they are not going to ask that question on a test.
Okay.
Because it's not that it's ambiguous here, but because they're expecting you to understand that there's an overriding thing there. If you have a conductor, there are charges that aren't being counted in the fact that you're saying all charges contribute to the electric field. A conductor brings with it its own group of charges inside the conductor that are continuously rearranging themselves until the electric field inside the conductor is 0. Does that make sense? So they wouldn't do that here because they're trying to isolate these 4 individual charges only. If they brought the conductor in there, they'd mess up a lot of stuff when it comes to the questions that are here. They just can't be asked because the conductor itself then is bringing charges with it. So the charges, so I'd have, I don't remember. And point P is right here. So this is kind of what, if I take the squiggly line out of there, if I asked you about the electric field at point P, then you know from the training we've had already that I would have to take a look at this distance and the influence on the electric field, and this distance and the influence on the electric field, this distance, and then this distance, and how all those affect the electric field at point P, right? It doesn't matter that the Gaussian surface is there. The electric field at point P is still the sum of all of those things. Does that make sense? So, and let's talk about that shell for just a minute, because Tyler's asking an important question, and
Shape of those squiggly lines was instead.
didn't really talk about it. So So this is going to take us a little bit away from what we've been talking about, but I think it's worth discussing.
Before you start, can I ask a question that was prevalent to the previous one you just answered?
Yes.
If
There. For just a moment, and I don't want to talk about a conductor first. Let's talk about an insulator. Let's say that this is an insulator that has a uniform charge spread around the sphere. So it's a sphere. I'm just looking at a subset of it. So the whole thing is positive Q, and so there's some kind of positive charge density that is spread out over the entire sphere. But again, it's an insulator. It's not a conductor. We okay so far? By definition, by application of Gauss's law, if I was to put a Gaussian surface, and it doesn't even matter where I put the surface, if I was to put the Gaussian surface somewhere inside this sphere, then by definition, the flux through the surface would have to be zero, because I'm enclosing no charge. But more than that, if the flux is zero, but I have a clear bounded surface area, at this moment, I couldn't easily take E out of the integral, because you could make the argument that, well, Mr. Sheldon, I don't think E is the same for every point on that surface. So you can't take it out of the integral, even though I know this whole thing is equal to zero. However, if I do, and I'm not trying to play hard and fast with the rules, but if I do center it so that it's now symmetrically centered inside the sphere, even if there is an electric field, it would have to be the same for all points in the sphere. So then I pull that out. I finish this off. And still show the electric field has to be zero. Now, you say, well, isn't that cheating because you made it symmetrical? Is it no longer zero if it's asymmetrical? No, because my result here is for actually a particular place, a distance r from the center. And I can make the sphere any size, starting from the very center, spreading outward. So that tells me that every single place inside this sphere must have an electric field of zero. But that seems to go against our understanding of this, at least to a certain degree, because, like you were saying, don't the charges on here kind of cause an electric field? Well, they must. So what's happening? How is this? What's going on? Let's consider a point charge right here. Clearly, charges that are located in this part of the sphere are going to apply an electric field here that's powerful because it's close to that. In fact, there's going to be a charge here that's really powerful because it's even closer, right? But there's also a charge over here. It's further away. It's going to apply a force this way, but it's not going to be quite as powerful because it's further away. Now, if you sum that over the entire sphere, you begin to recognize that over the entire sphere, half of the charges on this side, it's not quite half, right? It's less than half, but all of those charges are in closer proximity to the charge in the middle. They're applying a force purely in, let's get all this stuff out of the way, purely in this direction. But there's a lot more charge over here, but it's further away. Believe it or not, you can actually do the summation. Well, I can't, but you could do the summation, and you'd be able to show that anywhere in the sphere, the electric field is zero, even if you break your sphere up into multiple point charges. Now, actually doing that, that's a little bit of math I don't want to do with you guys. If you're up for it someday, maybe as an exercise in showing how math works, we could do it. But I'm not feeling it right now. What's interesting is this would be true whether this was positive or negative. If it was a negatively charged insulator, same would be true. It's just that the forces would be in the opposite direction. They'd be pulling it equally in all directions. I bring it up for a couple of reasons. One, hollow earth theorists. I just watched King Kong versus Godzilla the other day. And why not? It's on HBO Max. So, in watching it, King Kong ends up reigning supreme. And I don't want to spoil it for you guys, but if you haven't seen it yet, well, you've had your opportunity. So I have no trouble in saying that King Kong reigns supreme in the center of the earth. It's where his ancestors are from. And it shows him sitting on his throne or walking around this chill area where there's all this cool stuff and clearly a light source from somewhere, which I'm not sure how they figured that out yet, but how they figured out a light source inside the center of the earth.
Oh, yeah.
Now, well, there's no core. It's hollow earth.
What about the sun?
They're inside the earth. So I'm affecting the idea that it's probably pretty dark there. They entered through the North Pole, too, so it's not like there's a hole aimed at the sun to let light in. The truth is, this would behave the same way for gravity as it does for the electric field. That if you could hollow out the earth, the gravitational force on any particle inside the center of the earth would be zero. You have equal earth in all directions, is what it amounts to. So, and we talk about this in mechanics a little bit, but the truth is, once you get inside this shell, the uniformity of the shell is pulling you equally in all directions, even if you are asymmetrically located in the shell. And it has to do with the fact that you are closer to some charges, but there's a lot more charge that's further away, and it balances out perfectly, but only for a sphere. So because it's spherical, you get this effect. Yes?
Is there any particular reason that it's an insulator and not a conductor?
Yes, and I did that purposefully because with an insulator, those charged particles have to stay where they're placed. If I was to talk about this with a conductor, I have to be more careful about a conductor. And the reason I'm trying to be diplomatic here, the moment I turn this into a conductor, this charge here, creating an electric field, is going to influence the charges in the conductor, making them no longer symmetrically located about the sphere. So what's interesting, actually, I think, is that the charges have to change their arrangement if this was a conductor all of a sudden. And I've moved that charge over so it's asymmetric. It would have had field lines like so. I'm trying to draw them as carefully as I can to give you the effect you need. Now with the conductor in place, the field lines outside the sphere will still act as though the sphere is not there at all. Meaning the field lines will have a hiatus while they're in the sphere. There'll be no electric field inside here. But the charges in the conductor will have to distribute themselves in such a way that they produce electric field of 0 inside the conductor. And that has the effect of rearranging the charges on the outside so they produce the exact electric field you would expect if the charge were there by itself. So the field lines are not warped outside of the conducting shell. They have to provide the same amount of symmetry as you would normally expect, even if it was all perfectly centered and everything.
Would the charge like move at all? Like, let's say you place it inside like the sphere, like the conductor on the sphere, and it's like positive charge.
Which charge are you talking about?
Q. Like if you had an actual charge, like not a test charge, and you put it like asymmetrically inside the polysymmetric sphere, would it like be attracted to the side?
I don't know. I'm sorry, I just don't. Yeah.
Was it intentional that you made a super smash symbol?
Of course it was.
If you were to break like conductor, could you allow your final smash?
Definitely. Go ahead.
So we were talking like in the previous question about doing something like this, positive Q charge and a conducting thing. So with the inside, the electric field for we just talked about the insulator had an electric field of 0 IQ because of the symmetrical nature. So would that still be the case with the conductor or no?
I don't think so.
And if that isn't, then why in the previous FRQ question do we just kind of completely disregard the? I guess it's because we were using a shape instead of a charge.
Yep.
Okay.
So I do want to get back onto the FRQs, but I wanted to make sure we explored this enough to first understand that inside this shell, inside the spherical shell, you would get this electric field of 0 for an insulator. And that would be true regardless of what your force carrier was. So gravity or electric field would still be 0. So, Super Smash, I'm not going to... You don't know what Super Smash is?
My brother, I guess.
You got to run less. Go ahead.
So if it was a conductor, would the electric field at the Q phase still be 0?
If it was a conductor, would the electric field inside... Are you asking if the electric field inside this area would be 0?
Yeah.
No. Well, I want to say this differently. The electric field would still exist from the charge Q. That was there the whole time. But would there be an electric field inside here due to the charges on the conductor? And the answer would be no. The electric field inside here would still only be the electric field from this charge Q. The rearrangement of the charges in here would preserve this electric field so that it would stay this shape inside here, because it would have to in order for the electric field to remain 0 inside the conductor.
So it'd be 0 as well.
Right. It would not influence the electric field that's already inside there. So its contribution, the shell's contribution to the electric field inside the shell would still remain 0. But Q's contribution to the electric field would stay there. Okay. An example of what this would look like. Imagine a Gaussian surface where you had a very small dipole with one positive and one negative, but they're very close together, but you centered a Gaussian surface pretty far away from it. No matter where you are now on this surface, the distance from each of these charges to any point on the surface has got to be nearly equal. Enough so where the electric field at any of these points has got to be almost 0. And that would be true all around that surface. Now, this is a situation in which we could probably theorize right at this moment that the electric field is 0 at almost every single point on this surface. Our enclosed charge is 0. What really should bother you is that if I have another charge here, even if it's super powerful, the flux is still 0. It would have to be. Even though with just these charges, the electric field is probably 0 everywhere on the green circle. When I add this charge, that's not true, but as much as the field lines that pass through the area also exit the area. So any field line from that charge is going to have an equal contribution of both positive and negative flux. Yep.
Well, why, if we're talking about an individual point of the surface, why does that matter? Because we're not talking about going, oh, it's because it's conducting.
Well, and there's also there's something that you have to understand about the test writers. Consistent. So Gaussian shell has to be in the middle. That's not a Gaussian shell. I think I want a circle. There we go. I'm thinking sphere makes the most sense. You guys agree with that? That way I have a certain amount of uniform symmetry, meaning the shell is equidistant from any point on the surface of the conductor. Is that good? I'm expecting the conductor to have a to have a symmetrical electric field that comes away from it like rays off of a star. So that's going to be my start. And since it says derive, I have to do every part of our derivation here. I can't skimp out. So Q enclosed is the first part, and flux will be the second part, and they must be equal. Q enclosed is pretty easy. Looks to be positive Q, right? My surface encloses just the charged sphere, and the charged sphere has positive Q on it. Now, flux, a little more work. So let's do that over here. Flux is E dot dA. Now, the amount of work you have to show is not as much as you might think. You have to start here, and you probably, when it says derive, should make certain indications. Like, I think it's not too big of a step to say that you can do this in a step. An indication that the electric field is the same everywhere on the outside of the sphere. That's why we're pulling it out of the summation. Saying that the electric field and the area are always in the same direction everywhere on the sphere. That's the cosine 0 degrees. And then a summation of the total area for a closed and bounded surface. So I think you need steps here for the derivation, but you don't have to justify your steps. So I think starting here and going here is not too much. But don't jump at it. You need to show a derivation. To start from the first principle and work your way all the way until you have something appropriate. So now that I've done that, I can solve for the electric field. And you don't have to add this, but I'm adding it for right now. Good? All right. Any questions about what we've done there? Start with the surface. Separate your Gauss's law into two parts. Deal with how much Q is enclosed and your flux. And if you have to break up your surface into multiple surfaces, make sure it's totally enclosed. Question B, write an expression for the electric field at R is greater than C, at R between B and C, and R and less than A. So let's do the easy ones here. So this is part B. We know that when R is between B and C, the electric field has to be 0 because they're inside the conductor. That's talking about this location right here. Right? In a conductor, you don't have to justify it. Electric field 0 inside all conductors. Yes, sir? Okay, I don't mind going back. Yes, I do. I mind going back. But I will, because I want you to understand.
Why does the outer shell not influence at all?
Me looking at you as I didn't know I heard a question mark. Can you say that again?
Why does the outer shell not influence the electric field at all?
Does it enclose any charge? I didn't say it didn't influence it, but does it enclose any charge? Huh? Does the shell enclose any of the charge that's on the outer shell? No. So, it doesn't, how do I say this? I'm not saying it doesn't influence it, although it doesn't. What I'm saying is that if there's an influence, the influence has to be the same on every part of the shell, because it's equidistant away from the shell and symmetrical. Correct? All I'm saying on this portion of the derivation is that even if the outer shell does have something to do with the electric field, and I'm not saying it does, we're not doing anything wrong with what we've done for our assumptions here. I still believe that at this point, this point, this point, or this point, the electric field at all those points is probably the same value because of the symmetry of the system. I'm also saying that I'm pretty sure the electric field will be in the same direction as the area or the opposite direction of the area, but it will still be either cosine 0 or cosine 180, period. But it's most likely to be cosine 0, meaning the electric field points this way. I don't have to know that to be true, but I know it's not like at an angle like that. Right? Symmetrically, that's impossible.
Yeah.
And once I've established those, pulling this out of the integral is possible because the electric field is the same at all those points. Pulling this out, or setting this equal to 0, is because we identified the dot product influence on the problem. And now I'm left with just summing the size of the area, which I'm doing, 4 pi r squared, which is all that's left here. Follow me so far?
Yeah.
Now, it's not for you to decide why the electric field isn't affected by the outer shell. It's for Gauss's law to decide that. And Gauss's law has. That's all there is to it. So I guess the reply to you is that we showed mathematically, using everything we know about Gauss's law, that the electric field from the outer shell doesn't affect things inside the shell.
Oh, yeah, that makes sense.
Okay, because you think it makes sense now. But remember, the idea here is if this wasn't even there, would there be an electric field inside the shell? The answer would be no. Right? I'm enclosing no charge. This would have to be 0 no matter what. There's no flux. And all the rules we just applied on the electric field still apply, so we get electric field as 0. You following me?
Yeah.
Feel good about it?
I know. Wow.
Takes a little bit, but yeah, that is still true. You see, the thing I'm trying to say here is that I'm not the one saying that this charge on this shell produces no electric field inside the shell. I'm not saying that. I'm telling you that Gauss's law proves that to be true. Gauss's law is the law, though. I don't know why this is true. I want to be very clear about that, too. I don't know why that's true. But it is. Now, I think I do know why it's true, but I don't want to go into it. I'm telling you I have a theory. But this law has to be absolute. Okay?
Yeah.
All right, moving on. Now, so I think we got that. We also have that R is less than A. I think that one's pretty easy. I don't think I have to convince any of you that if we're inside the other conductor, electric field is going to be 0. That good too? So all that's left is if we're outside the conductor, the electric field out there, which means I'm thinking of another Gaussian surface like so. Does that work okay? So this is R is greater than C. Do I really have to redo everything It doesn't ask me to. It just says write expressions. Can I write the expressions that when R is greater than C, the electric field has to be 2Q over 4 pi epsilon naught R squared? Nothing on the right side of this is any different. The only thing that's actually different is that I enclose twice as much charge now. Is that okay? Or do you need more explanation than that? Because AP doesn't need any more explanation than that. That doesn't mean that you don't. But I'm just repeating the Gauss's law process. Meaning, I'm looking at how much charge is enclosed. It's now 2Q. Because how much charge is inside the bigger green circle? Do you guys see that it's 2Q? We sure? I'm trying not to talk too fast, but... Now, I'm still going to have all the other things about the electric field that I have to go through. Is the electric field the same at all of these points on the surface of my Gaussian shell? I believe so. I've set it up symmetrically so that it will be. Is the electric field in that direction? I think so. It seems reasonable. Is the area also in that direction? Yes, it is. It has to be because it's a sphere. So cosine of 0 degrees. What's the area of this sphere? 4 pi r squared, where r is greater than c. It's going to have to give me that. We okay to move on? Because now's when it gets interesting. On the axis below, sketch a graph of the electric field, magnitude E versus distance r from the center. We've done this already, but I think it's worth doing again. So, interestingly enough, when you consider doing this, do you want to start from the outside in or the inside out? It doesn't really matter to me. Electric field, I tend to feel like we should go inside out. But I know those two have to be 0. Right? Has to be. Now, in this space, the electric field is KQ over R squared. Just replacing the 1 over 4 pi epsilon naught with K. And in this space, the electric field is 2KQ over R squared. Correct? So, here's the thing. I don't really know how to or where to put all this, because we don't know what B or C is. But we know from A to B, we're going to have a reduction in the electric field as 1 over R squared. But then suddenly Q jumps and doubles, while the distance away increases by a small amount. I would expect the electric field then to increase some and then drop again. Right? Q doubles. So the electric field, unless R has a big enough change to compensate for the Q doubling, there's probably a sudden increase in the electric field. Yep. It could. You could line up the distances to do that. But we don't know if that's true or not. And so I would encourage you to say they made those small for a reason. And they put a 2C out here to drive the point home a bit. You follow what I'm saying? So I would anticipate that they want that doubling of the charge to offset the distances enough for you to realize the electric field must increase. And it's to try and mess up what you do next. I want you to know that too. Because the next thing is the electric potential. And they're thinking you're going to screw this up. I think for electric potential, we should work from the outside in. Because you can't just take this at face value. Oops. You have to remember where you got that. I think it's better for you guys to realize that this is the shape of the electric potential. but that was garnered or derived by thinking about how much work is done moving a point charge from someplace far away to someplace close to zero. So let me say this next thing for all of you who are going to mess this up on the next test and be unhappy with your 3 out of 15. That now would be the moment to write things down. Because I don't want to say this rudely, but you understand that it's going to be in the subtext here, and you're going to think that you might have maybe even a tenuous grasp on this. You know, the next question is they're all the same, but they're not all the same, right? You get one, it just throws you a little bit. So the question you have to ask yourself is, this should be the shape of the curve, a 1 over r. But you also need to be aware is, when are you doing work? Well, I am doing work right up until I hit the side of that metal. So I know the potential should be going up, should be increasing all the way until I hit the metal side. And then the electric field is 0, which means even though there's a difference in the electric field on one side or the other, that's not what the electric potential is about, which means the electric potential should be flat here. Because the electric field is 0 inside, it takes no work to go up. So when you're trying to draw this graph, anytime the electric field is 0, no work is done. Now, for some of you, that's got to freak you out a little bit, because you're like, well, wait. If I just plug in B or C in this expression for the electric potential, I would get different values here or here. Because B is smaller. Shouldn't that mean the electric potential is bigger? The answer is no, because that's not how we solved for the electric potential. This formula came from originally having 1 over infinity minus 1 over r. We talked about the work done in getting there. And that has to be accepted here too. So no, I can't just put in the electric potential here and here and show that it increases. This point, to get to this point, this far away from the center, I had to do work for only part of the motion. No work was done in going from C to B, so for this time it's flat. So no. And that's what the important, another thing too is, if they ask for what the electric potential is at B, you better not put B in here. The electric potential at point B would be Q over 4 pi epsilon naught, 2Q over 4 pi epsilon naught C. That would be the electric potential at point B. Because this would be the electric potential that you would get in going from infinity to C. And the electric potential didn't change between here. Let me say all that over again, because I want to make sure you got this in your notes. But the electric potential is about work done. You can't just plug it into the formula. It's about work done. So the amount of work in going from here to here, meaning from infinity to C, can be given to us from this relationship. Because it was a direct push from infinity all the way to C with no interruption. But this also has to be the same at point B and point C, because there's no change in the electric potential from C to B. Now, some of you will say, but Mr. Shelton, if I plug in the formula at point B, wouldn't I get this? I know some of you will say that. The only way to get this is if we started at infinity and went right to there. But we didn't do that. We came up against this surface where the electric field was 0. So we didn't do work the whole time, which is why this is not the electric potential at B. This is. Yes, sir?
In terms of like the summation, would it be like 2 summations, like all the way to C and the second summation from C to B?
Yeah, you could, but we know the summation from C to B is going to net 0 change in potential. Is that all right? So from this point forward, though, the rest of this is actually, I think, pretty easy because the electric potential increases again linear, or not, as an inverse. Oops. As an inverse. Until we hit the wall there, and then it stays the same again. Any place where the electric field is 0, the electric potential is flat. Yep.
How can it go from industrial to
It does not affect the electric potential. And it's because it would not change how much work had to be done. And this is where we tend to have our issue. Because here's the thing. You cannot use the basic formula for electric potential. This is our basic formula for electric potential, remember? I'll just put K here. So this is our basic formula for electric potential. You could not use it to find the electric potential there. You can't. You can't apply it that way. You can't just pick a point in space and apply this formula. This formula was derived by having an unimpeded change from infinity to a location in space. And there's no way to get to this spot in space without also going through the shell first. That's why that equation doesn't apply there. And why it doesn't matter that the inside is Q. Does everybody understand? I mean, if the outer shell was 2Q and there was no inner shell at all, the electric potential inside there would all be based on what it took to get there. Nothing about what's inside. Okay. Determine the potential at R equals B. I think we've done that already, but just to make sure, it's whatever it is at C. Yep.
So would that also apply for the building, for example?
Yeah. Now, the truth is, this is what it is at when we go to B. Now, calculating it from B to A, we'd have to integrate. Because we now have a change, we have to integrate and add that amount of work here. Meaning, this is the potential at B. So if I want to find out what the potential is, say, at A, and that's a really good question. So if you guys want, this is a teachable moment. If I want to find the potential at A, the surface of the other sphere, this is the starting point. I can calculate the change in potential from B to A. And now put in QK over R dr. And do that, R squared dr. Remember, this is the integral of E dot dx. That's how you find a change in potential. But I would have to add whatever this change in potential is to the potential I already had. Now, in all the years all the years that they've asked these kinds of questions, they've not asked anybody to do that, but that's not outside our curriculum. They could. They're asking this question for that very same purpose, to make sure you understand you can't just blindly apply this to any point in space. You can't. You can only apply that to points in space that you can get to from infinity without having any kind of other gaps in the electric field. Have I beat that dead horse enough? Oh, good. So that means we can move on to something else now? Oh, great. That's this whole problem, right? We're done with that one? Fan.